the idea of this exercise was to get us to practice a little bit of the using the active topology. And as you can see during this exercise, it can be very helpful because most of the time that you're doing design, it's, the pre-development, post-development condition, you got to make sure that your post-development runoff is not, the peak runoff is not greater than the existing pre-development. So this would be something that you could actually use in your projects often. All right, so we're able to use that active topology to show what it's like to include or not that parking lot. And we did a few scenarios. So the very first one was the existing system. And when we did that, we were generating a runoff of 4.5 cubic feet per second. We then run the post-development, and the peak flow had gone up to 5.57, and that increase, even though it didn't seem like it was very large, had some implications on our profiles and on how some of these pipes were, let me put this velocity here, how the pipes were affected. All right, so here we have a little legend for pipe velocity. We could do also pipe flow, but as we saw, the pipe flow is not too different. But here we can see that even in the pre-development, we had some high flows, high velocities here. So between 6 and 8 feet per second. So let's take a look at what's actually going on there. We could do any of those, but let's focus on I2L to the outlet. So let's take a look at that first in the pre-development. Okay, so even before we put in that parking lot, these pipes were being surcharged. So we had PO1, P2R, and P2L. So we had that no overflows, but surcharging of those pipes. And then when we did the post-development, that got a little bit worse, right? So this profile gets cut a little bit there because we got rid of that inlet, right? And then went to IPL1. So if we wanted to see the full run of that profile, we can do this, but we can basically see the same effect, that it's definitely time to upsize those. So that's what we did, and I think by now you guys are going to be able to design systems with this automated design feature in your sleep, because we've done it so many times and we're so familiar with it. So we went to the alternatives. Where did my design alternative go? By the way, if you sometimes this gets overwhelming, you can use these buttons to collapse all or expand all. That's what those buttons are for. Okay, so base design constraints. So we decided that the root of the problem seemed to be here. So we chose to upsize those two pipes, and we also said, and go ahead and design the new pipes as well, those PPL, so parking lot pipe. All right, so we set to do that, and we also allowed modification of the inverts associated with those pipes so that the slope could be improved. And also we said, if you find that the inlets are not sufficient, go ahead and modify those inlet openings as well. All right, and what was the result of that design? Well, we can see here our velocities improved a little bit. Let's take a look at the profile first. um, get a better idea. Take those annotation labels off. So through our magic, we were able to make this um, start charging disappear. And remember, we designed for the 10-year storm in this exercise, and we're just going to check it against what would happen in a 100-year storm. We just want to make sure we don't get any water spilling out of these catch basins. Okay, so what did it actually do? Well, we uh, could take a look at the scenario comparison and look at the individual differences. And in terms of the pipes, we can see that, um, open up this a little so we can see the new pipes in the parking lot where a couple of them went from 12 to 15 inch. So we increased those diameters and modified the slopes and also basically increased the length of the grate, and in this case of IPL1, increased the curb opening by quite a bit. It was 4 and it went up to 15.7. All right, so that's all the magic that happened to make that work a little bit better. So let's answer some of the questions that are asked at the end of the workshop. What is the maximum spread in the system? Now we know to look for the field called spread. And we can see that for the redesign in the 10-year storm, it's 7.8. So it still meets the requirement of 8 feet of spread. So we're happy with that. Just to see what it was like before we redesigned it, it was 15.4. So definitely violating, and that's why it was IPL1 that the inlet size was increased significantly. Okay, so we did that, and we said, okay, um, no surcharging, and the spread is good in all our inlets for that redesign. Now let's check what happens to that design if I uh, check a 100-year storm. And here, I'm going to open up that profile. You can see that there would be surcharging, but there wouldn't be any overflows. So if your local regulatory agency would accept that, then you could stick with this design. If you were asked to actually design for a 100-year storm event, which might not be the case, but um, then you would make the appropriate modifications. Okay. Um, so how much of the system pressurizes during this scenario? Well, visually we can see this pipe right here, right? It's pressurized. Let's look at the annotation labels. So P2R fully pressurizes. If you want to see it in a table, you can always go to the conduit table and look at the depth over rise. Well, I guess when you go above 100%, it shows that way, but we can see here the flow divided by the capacity. It's exceeded in this pipe right here. And we can also see the profile description as it being pressure. In fact, this one as well. Okay. So rational method is used to compute. The question gives you 3 different options. Peak flow from a catchment, average flow from a catchment, or a runoff hydrograph from a catchment. Calculate only the peak flow. Now, the question number 4, you should create a new StormCAD file for each different design option. True or false? False, correct. That's That's the idea behind the scenarios, right? So that you can do all the analysis in one file and be able to make comparisons. What is the typical range of values for the rational C coefficient? So theoretically it's 0 to 1 because it's really, kind of like what percentage of the of the rainfall becomes runoff. So it's either all or nothing, all being 100% or 1, nothing being 0. But in reality, there's always, some rainfall loss to ponding, or, it evaporates before it gets to its end. So between like 90% and 1 or 10%, so 0.1 and 0.9. Okay, so we looked at using the active topology tool, and the effect of it, I like to remind our students, it's, if you want something to appear or disappear from your model, so you're not really making it disappear, you're just kind of hiding it, right? So if you don't want to include elements in a particular scenario, you can turn them off by using active topology, right? And the last question, best time to make use of prototypes. We use prototypes a lot at the beginning when we were laying out elements. And if you're going to do a lot of manual input, then before you draw anything, you want to do the prototypes, right? Because if you do everything by hand and then you create a prototype, it doesn't do anything. It's only before you do that. If it's too late, then at that point you might as well just modify everything on the flex tables.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.